Welcome to your deep dive. Today we're diving into the world of astronomy.
Yeah,
We're going to be guided by your selections from astronomy, the solar system, and beyond. Get ready to have your mind blown wide open, because this book is packed with fascinating stuff.
absolutely. From our neighboring planets to the echoes of the Big Bang itself, this book covers it all. I'm excited to see what sparks your curiosity today.
Me too. You know how sometimes you need that reminder that Earth is just a tiny part of something much, much bigger? I feel like astronomy really puts things in perspective.
Yeah.
So let's start with our cosmic address. Where do we even fit into the grand scheme of things?
It really is a humbling shift in perspective, right? So picture this. You zoom out from your house, past Earth and our moon, further and further until our entire solar system is just a speck. We find ourselves about two-thirds of the way out from the center of a vast spiral galaxy, the Milky Way.
So when we talk about the Milky Way having those graceful spiral arms, our entire solar system is tucked into one of those arms, with light years of space between us and the next star over. It's almost impossible to wrap your head around.
It really is. And that's not even the crazy part. Our galaxy, as mind-bogglingly huge as it is just one of billions upon billions scattered throughout the universe.
Okay, that's officially too much for my brain to handle right now. But before we even attempt to think about those distances, let's talk about how astronomers gather information about objects so incredibly far away. I mean, we're talking about things that are light years away. How do we even know they exist, let alone what they're made of?
Right, so that's where telescopes come in. They're our eyes on the cosmos, gathering the faintest glimmers of light from these distant objects. You can think of them like light buckets. The bigger the mirror, the more light they gather, and the fainter the objects they can see.
So it's a cosmic game of bigger is better when it comes to telescope.
In a way, yeah. But there's a little more to it than that. You see, visible light, the kind our eyes detect, is only a tiny sliver of the entire electromagnetic spectrum. There are also radio waves, infrared, ultraviolet, X-rays, and gamma rays, all carrying unique information about the universe.
So are you saying that there are telescopes out there that can see these other kinds of light?
Exactly. And each type of telescope reveals something different. For example, the Chandra X-ray Observatory. It orbits Earth, capturing X-rays emitted from incredibly energetic environments, like the remnants of exploded stars and those mysterious cosmic monsters, black holes.
Okay, that is seriously cool. We're not just talking pretty pictures here, but actual data that helps us understand some of the most powerful events in the universe.
Yeah.
So we've got these amazing telescopes gathering light from across the universe, but how do we make sense of it all?
Well, that's where things get even more fascinating. Astronomers have figured out how to decipher starlight to unlock a star's secrets, its temperature, composition, even how fast it's moving.
Wait, hold on.
Yeah.
You're telling me that by simply analyzing the light from a star that's light years away, we can tell what it's made of? That's like some sort of cosmic magic trick?
Right.
How is that even possible?
Yeah, it's definitely not magic, though it certainly feels like it sometimes. It all boils down to the interaction between light and matter, specifically atoms. Think of an atom like a tiny solar system, with electrons orbiting a nucleus. These electrons can only exist at specific energy levels, right? When an atom absorbs light, its electrons jump to higher energy levels, and when they fall back down, they release light at very specific wavelengths.
Okay, I'm following so far. We've got electrons jumping between energy levels, absorbing and emitting light. But how does that help us understand a star that's millions of miles away?
Here's the key. Every single element, whether it's the hydrogen that makes up most stars, the helium we put in balloons, or something more exotic, has a unique set of these energy levels, like a fingerprint.
So it's like each element has its own light signature.
Exactly. Astronomers use an instrument called a spectrograph to split starlight into its component wavelengths.
Okay.
This reveals the telltale fingerprints, called spectral lines, within the star's light. These spectral lines act like a barcode, revealing the precise elements present in the star's atmosphere.
Wow. That's incredible. And to think we can do all of this without ever having to leave Earth. It's like the universe is speaking to us through this language of light if we only know how to listen.
Yeah.
Now, our deep dive also mentioned something called the Doppler effect. How does that tie into all of this?
Ah, the Doppler effect.
Yeah.
So the Doppler effect is all about motion and how it affects waves. You know how a siren sounds higher pitched when it's approaching and lower pitched as it moves away?
Yeah.
That's the Doppler effect. Light waves behave in a similar way.
So if a star is moving towards us, Its light waves get compressed, shifting towards the bluer end of the spectrum, and if it's moving away, the light waves stretch, causing a redshift, like a
Yeah.
cosmic game of red light, green light.
You've got it. By carefully measuring these subtle shifts in the spectral lines, astronomers can pinpoint whether a star is moving toward or away from us, and even determine its speed. It's a powerful tool for understanding the movements of stars and galaxies.
It's like we've unlocked a secret code, allowing us to decipher the movements of objects across vast cosmic distances. This is already blowing my mind, and we haven't even left our own solar system yet. Speaking of which, what can you tell us about our cosmic neighborhood? What awaits us as we venture out to explore the other planets and celestial objects that share our corner of the galaxy?
Yeah, we've got a whole planetary playground just waiting to be explored. Why don't we start with our closest neighbors in the inner solar system, the uh, the terrestrial planets.
Terrestrial meaning Earth-like, right? So Mercury, Venus, Mars, and of course Earth. But even though they're made of similar stuff, rock and metal Earth seems to be the oddball out, with its life-filled oceans, breathable atmosphere, you know what I mean? Our source material mentioned that size plays a big part in how a planet evolves. So what makes Earth so special in that regard?
You hit the nail on the head. Size is crucial for planets, just as it is for stars. Larger planets can hold on to their internal heat for much longer, and that heat fuels geological activity, shapes their atmospheres. Earth, being the largest of the terrestrial planets, has retained enough heat to maintain a molten core. Think of it as a planet-sized engine that drives plate tectonics and generates a protective magnetic field.
That internal engine keeps things interesting, shaping Earth's surface and creating a dynamic atmosphere. Okay, that makes sense for Earth. But what about the other terrestrial planets? What stories do their surfaces and atmospheres tell?
Let's take Venus, for example. Venus is shrouded in these thick, reflective clouds, and while those clouds might look beautiful from a distance, they trap heat, creating a runaway greenhouse effect.
So Venus is like a cautionary tale about what happens when the greenhouse effect goes out of control.
Exactly. Venus is the hottest planet in our solar system, even hotter than Mercury, which is closer to the sun.
Wow, that's scorching. Our source material also mentioned that Venus is a volcanic hotspot. Is that related to the whole runaway greenhouse thing?
It's more about Venus having a surprisingly young surface, geologically speaking. Imagine this. The entire planet seems to have been resurfaced by volcanic activity within the last half-billion years. There's evidence of corona, these massive circular regions where molten rock is pushed up from below, creating a completely different kind of tectonic activity than what we see on Earth.
So Venus is like a giant pressure cooker, with volcanoes constantly reshaping its surface. It's amazing how two planets can be so different, even when they're made of essentially the same stuff. But let's move on to a planet that's captured human imagination for centuries, Mars. Is there really any hope for water or even life on the red planet?
Mars is a study in contrasts. It has giant extinct volcanoes like Olympus Mons, 3 times taller than Mount Everest, and a colossal canyon system, Valles Marineris, that dwarfs the Grand Canyon. But the most exciting features are the signs of past water-dried-up riverbeds, ancient lake beds, and minerals that could only have formed in the presence of liquid water.
It's like Mars is a planet that lost its way, a once warmer, wetter world that transformed into the cold, dry desert we see today. What happened to all that water? Did it just evaporate into space?
That's a question that keeps planetary scientists up at night. There's evidence suggesting Mars had a thicker atmosphere billions of years ago, one that could have supported liquid water on its surface. But over time, that atmosphere thinned, likely stripped away by the solar wind, leaving Mars a shadow of its former self.
It's a bit of a planetary tragedy when you think about it, the lost oceans of Mars. But our source material did say there's still water on Mars, right?
There is, but most of it is locked up as ice, mainly in the polar caps and possibly as permafrost beneath the surface. There's even evidence from the Mars rovers of hydrated minerals, nicknamed blueberries, that suggest water might have played a role in shaping the Martian landscape more recently than we thought.
It's exciting to think that there might be pockets of ice or even liquid water hidden beneath Mars's surface, just waiting to be discovered.
Now, before we journey to the outer planets, I have to ask about our very own celestial companion, the Moon. What can you tell us about its formation and how it ended up orbiting Earth?
Ah, the moon. The moon is like a silent guardian, a constant presence in our sky, and its history is deeply intertwined with Earth's. Take a look at its heavily cratered surface that tells a tale of intense bombardment in the early solar system, and those dark, smooth plains we call Maria. Those are solidified lava flows from a time when the moon was a much more volcanically active place.
So the Moon has a fiery past, but how did it become Earth's partner in the first place? The leading theory is a giant impact, a cosmic billiards ball collision of epic proportions. Imagine this, a Mars-sized object slammed into the early Earth, ejecting a massive amount of debris that eventually coalesced to form the Moon.
Wow, a cosmic smash-up. It makes you wonder what other dramatic events have shaped our solar system over billions of years. Speaking of dramatic, let's head out to the outer solar system where we find the gas giants Jupiter, Saturn, Uranus, and Neptune. These planets are in a completely different weight class compared to the rocky terrestrial worlds we've been discussing. What sets them apart?
Their composition is key. Jupiter and Saturn, the largest of the bunch, are composed mostly of hydrogen and helium, the lightest and most abundant elements in the universe. These gases, pulled in by immense gravity, create incredibly dense and turbulent atmospheres, with pressures and temperatures far beyond anything we experience here on Earth.
So instead of solid surfaces, we're talking about layers upon layers of swirling gas, maybe with a small, rocky core deep down. It's hard to imagine a more alien landscape. And what about those rings? They're some of the most breathtaking sights in our solar system.
You're right, they're truly spectacular. Saturn's rings are the most famous, but all four gas giants have ring systems, though the others are much fainter. These rings aren't solid structures, but rather countless icy particles, ranging in size from tiny dust grains to mountain-sized boulders, all orbiting the planet like miniature moons.
It's amazing to think about those countless particles, each one with its own story, all caught in this intricate cosmic dance. But are these rings ancient relics from the early solar system, or are they being constantly replenished?
That's a great question. The ring systems we see today are surprisingly young in cosmic terms. They're constantly being bombarded by micrometeoroids and debris from comets and asteroids, which grinds down the existing particles and creates new ones.
So it's like a cosmic recycling program with collisions constantly shaping and reshaping these rings. But before we get lost in those rings, you mentioned that the gas giants also have some pretty incredible moons. What can you tell us about those?
Oh, the moons are a world unto themselves. Jupiter alone has four large moons, Io, Europa, Ganymede, and Callisto, that were first observed by Galileo in the 17th century, hence their name, the Galilean moons. Each of these moons has its own unique character and story to tell. Io, for instance, is the most volcanically active body in our solar system, constantly erupting with plumes of sulfur.
That's one volatile moon. What about the others?
Well, Europa is a real standout. Imagine a moon with a hidden ocean of liquid water beneath its icy surface, an ocean that might contain more water than all of Earth's oceans combined. Some scientists believe that Europa's ocean could potentially harbor life. Then there's Ganymede, the largest moon in the solar system. It's even bigger than the planet Mercury. And finally, there's Callisto, a heavily cratered world that might have the oldest surface in the solar system.
It sounds like these moons are planets in their own right, some even more fascinating than the gas giants they orbit. What about Saturn's moons? Are there any that stand out in that crowd?
Saturn has a real gem in Titan. It's the only moon in the solar system with a thick atmosphere, one that's even denser than Earth's. But instead of water, Titan's rivers, lakes, and seas are filled with liquid methane and ethane.
So Titan is like an alien world right out of science fiction.
It really is. The landscape is sculpted by hydrocarbon rain, and there are even methane-based weather cycles. It's incredible. Now, we can't forget about Uranus and Neptune, often called the ice giants.
Right.
What makes them different from their larger siblings, Jupiter and Saturn?
Good catch. Uranus and Neptune are smaller and colder than Jupiter and Saturn, and they contain a higher proportion of heavier elements like water, ammonia, and methane. These ices, which aren't ice as we know it, but rather dense fluids under immense pressure, give these planets their distinctive bluish-green hues.
Exactly. And just like their larger siblings, they have rings and moons. Uranus sports a system of very faint dark rings, and its moons are named after characters from Shakespeare's plays. Neptune's rings are also quite faint and clumpy, and its largest moon, Triton, is unique because it orbits the planet in the opposite direction of Neptune's rotation, a retrograde orbit.
It's like Triton is a rebellious teenager going against the flow. It seems like every corner of our solar system holds a new surprise.
But speaking of surprises, I have to ask about Pluto. It got demoted from planet status a while back, and I know people still have strong feelings about that. So what's the deal with Pluto? Why isn't it considered a planet anymore?
Pluto's demotion caused quite a stir, but it boiled down to a matter of definition. In 2006, the International Astronomical Union decided to clarify what constitutes a planet, and they established three main criteria. First, a planet has to orbit the sun. Second, it must be massive enough for its own gravity to pull it into a roughly spherical shape. And third, it has to have cleared its orbital neighborhood of other objects, So Pluto met the first two criteria, but not the third.
That's right. Pluto shares its orbital space with other icy bodies in the Kuiper Belt, a region beyond Neptune that's teeming with remnants from the early solar system.
So even though Pluto got reclassified, it's still a fascinating world.
Absolutely, it's a dwarf planet with a heart-shaped glacier and 5 known moons. It's a reminder that our solar system is full of surprises. But as fascinating as the planets and moons are, they're just pieces of a much bigger puzzle, the story how our solar system formed.
That's right. All these objects, the planets, moons, asteroids, comets, they all originated from the same cosmic building blocks. So how did it all begin? How did our solar system arise from the chaos of space?
So you're ready to tackle the big picture now, huh? Our solar system's birth story. Okay, buckle up. The prevailing theory is called the solar nebula hypothesis. Basically, it proposes that our sun, the planets, moons, everything, all of it, originated from a gigantic rotating cloud of gas and dust.
I'm trying to picture it. This swirling cloud of cosmic dust transforming into our incredibly intricate solar system. It's mind-boggling how something so vast and complex could arise from something that initially seems so simple.
Yep, it's a process that unfolds over eons, a delicate dance of gravity, matter, and time. Think about it. Gravity starts to pull together the gas and dust in this massive cloud, the solar nebula. As the cloud collapses, it begins to spin faster and faster, naturally flattening into a spinning disk with a protostar forming at its center, our very own sun in its infancy.
So our solar system started as this flat spinning disk of gas and dust. It's incredible to think that something recognizable as our solar system emerged from that.
It is. And within this disk, something amazing starts to happen. Tiny particles collide and stick together, gradually clumping together through a process called accretion.
So it's like a cosmic snowball effect. These tiny particles gradually attract more and more material, growing larger and larger until they become planetesimals, the building blocks of planets. It's starting to make sense.
That's exactly it. It's a fascinating process, right? And there's another crucial factor at play here: temperature. The inner region of this disk, closer to the protosun, is much hotter than the outer regions. This temperature gradient dictates what kind of materials can condense out of the gas and dust.
Ah, so this temperature difference is the key to why we have rocky planets near the sun and gas giants farther out.
Precisely. In the scorching heat of the inner solar system, only heavy elements like rock and metal could withstand the temperatures and solidify. This led to the formation of the rocky terrestrial planets: Mercury, Venus, Earth, and Mars.
It's like a cosmic sorting machine. The inner planets formed from the heavier stuff, while the outer regions were left with the lighter elements.
Now you're getting it. The outer regions of the disk were much cooler, allowing lighter elements like hydrogen and helium to remain in their gaseous state. And since these lighter elements were far more abundant, they formed these massive planets: Jupiter, Saturn, Uranus, and Neptune, the gas giants we marvel at today.
It all comes down to which elements could condense out of that swirling disk of dust and gas, depending on their distance from the sun. That explains the makeup and location of our planets. What about all the leftover bits and pieces, the cosmic leftovers that didn't become part of planets or moons? I'm talking about asteroids and comets. What can they tell us about the early solar system?
They're time capsules, my friend. Remnants from that primordial cloud asteroids, found mostly in the asteroid belt between Mars and Jupiter, are composed primarily of rock and metal, hinting at their formation in that hotter inner region of the early solar system.
So asteroids are like the rubble left over from the construction of the inner rocky planets.
A perfect analogy. Now, comets, on the other hand, are like cosmic snowballs. They formed in the much colder outer reaches of the solar nebula and are made of ices: water ice, frozen carbon dioxide, ammonia, methane mixed with rock and dust.
And these dirty snowballs become those magnificent comets with their glowing tails when they get close to the sun.
Exactly. As a comet approaches the sun, its ices begin to vaporize, releasing gas and dust that create those iconic tails. It's like a cosmic fireworks display, and each one offers a glimpse into the composition of the early solar system.
So we've explored the planets, moons, and even the leftovers from our solar system's formation, but we haven't given enough attention to the star of the show, our very own sun. It's more than just a source of light and warmth. It's a powerhouse that drives our entire solar system. What can you tell us about our nearest star?
The sun is a fascinating object. It's not a solid ball of fire, as it might appear, but rather a gigantic sphere of plasma, a state of matter where electrons are stripped away from atoms, creating a superheated, electrically charged gas. At its core, the temperature and pressure are almost unimaginable. Millions of degrees and billions of times the pressure of Earth's atmosphere.
Those conditions sound intense. It's like a giant fusion reactor.
You've got it. That's exactly what's happening. Deep within the sun's core, hydrogen atoms are being forced together under immense pressure, fusing to create helium and releasing a truly mind-boggling amount of energy in the process, the very energy that sustains life here on Earth.
And that energy travels all the way from the sun's core out through its various layers and eventually reaches us here on Earth.
Yeah. It's a journey that can take hundreds of thousands of years as photons, particles of light, bounce around within the sun's interior before finally escaping into space. It's amazing to think that the sunlight we enjoy every day is the result of processes that occurred deep within the sun's core eons ago.
That's incredible. But the sun isn't just this constant, unchanging ball of plasma. It goes through its own cycles and eruptions, right? What can you tell us about those? Do they affect Earth?
Right. The sun is much more dynamic than it appears. Its magnetic field is constantly in flux, creating sunspots, solar flares, and coronal mass ejections, all of which can have tangible effects here on Earth. Sunspots, for example, are cooler, darker regions on the sun's surface that are associated with intense magnetic activity.
So when we see those dark spots on the sun, it's actually a sign of intense magnetic activity.
Precisely. And sometimes these regions can release massive bursts of energy known as solar flares, like a sudden eruption of energy that sends radiation hurtling through space. If a powerful solar flare were to hit Earth, it could disrupt communications, satellites, even power grids.
That's a little unnerving, so it's like a cosmic game of chance. We hope that those solar storms miss us.
In a way, yeah, but we're getting better at predicting and preparing for them.
Mm-hmm.
And it's not all bad news. These solar storms can also trigger some of the most beautiful sights in our sky. The auroras, those shimmering curtains of light, the northern and southern lights, occur when charged particles from the sun interact with Earth's atmosphere.
It's a good reminder that even though the sun is millions of miles away, we're inextricably linked to it. Our existence depends on it. But we've been focusing on our little corner of the galaxy, and I know there's a whole universe out there. What lies beyond our solar system, and how do we even begin to understand something so vast?
That's where we shift from exploring our own cosmic backyard to pondering the grandest scales imaginable. Our source material talks about our galaxy, the Milky Way, having a disk and a spherical component. It sounds like we need to broaden our perspective, you know? Tell me, what comes to your mind when you try to picture the Milky Way?
When I try to picture our galaxy, I think of those stunning images of a spiral galaxy, a central bulge surrounded by these majestic spiral arms, almost like a cosmic pinwheel. But how do astronomers even begin to map something that vast? It's not like we can just fly outside of it and take a picture.
You're absolutely right. It's a remarkable feat of deduction and observation. Imagine this. You're trying to map a vast forest, but you can only see the trees immediately around you. Astronomers face a similar challenge when mapping the Milky Way.
So how do they do it? How do they see through the cosmic clutter?
Well, it involves piecing together information from various sources and wavelengths of light. We can map the positions of nearby stars using telescopes that detect visible light. But just like dense foliage can obscure our view in a forest, gas and dust clouds can block our view of distant parts of the galaxy. That's where radio telescopes come in.
Because radio waves can penetrate those dust clouds.
Exactly. Radio waves have longer wavelengths than visible light, allowing them to pass through those obscuring clouds. They allow us to peer into the heart of the Milky Way and reveal the structure of its spiral arms. It's like using different kinds of flashlights to illuminate a dark room.
That makes sense. By using different telescopes and analyzing different wavelengths of light, we get a more complete picture of our galaxy. Our source material also mentions something called stellar populations. What are those, and how do they help us understand the Milky Way?
Stellar populations are groups of stars that share similar characteristics, like age and chemical composition. Astronomers have discovered that the stars in the Milky Way's halo, that spherical component we talked about, are generally much older and contain fewer heavy elements compared to stars in the galactic disk where our sun resides.
So it's like the halo stars are the Milky Way's elders, holding clues to the galaxy's early history.
That's a great way to put it. These halo stars, known as population 2 stars, formed early in the galaxy's history, before generations of stars had a chance to create heavier elements and scatter them into space.
What about the stars in the disk, like our sun?
Those are known as population I stars, and they're comparatively younger and richer in heavier elements, which astronomers call metals. This difference in composition tells us that the Milky Way didn't form all at once. The halo, with its ancient stars, formed first, followed by the disk as the galaxy evolved and flattened into the shape we recognize today.
It's fascinating to think that our galaxy has such a long and complex history, with stars of different ages telling different parts of the story. Our source material also mentioned that the Milky Way hasn't always existed in isolation. It's been shaped by collisions with other galaxies.
You're right, the Milky Way isn't just a static island in space. It's constantly interacting with its surroundings, particularly with smaller dwarf galaxies. Over billions of years, it has captured and cannibalized numerous dwarf galaxies, leaving behind streams of stars that stretch across the sky. There's even evidence suggesting that our Milky Way is currently merging with a dwarf galaxy called the Sagittarius Dwarf Spheroidal Galaxy.
It's a cosmic feeding frenzy out there. It's amazing how dynamic our universe is, galaxies constantly colliding and merging.
It is. And these collisions have profound effects on the galaxies involved. When galaxies collide, their gas clouds can get compressed, triggering a burst of star formation. These starburst galaxies are incredibly luminous, shining brilliantly as they churn out new stars at a remarkable rate.
It's like a cosmic fireworks display, with these collisions sparking the birth of new stars. But let's zoom out even further. We've talked about our galaxy, the Milky Way, but it's just one of billions upon billions of galaxies in the observable universe. What can you tell us about those distant galaxies? How do we even know how far away they are?
That's where redshift comes in. Do you remember the Doppler effect we talked about earlier? How the sound of a siren changes pitch as it moves towards and away from you?
Yes, the sound waves get compressed as the siren approaches, making the pitch higher, and they stretch out as it moves away, making the pitch lower.
Light waves behave similarly. When an object in space is moving away from us, its light waves get stretched out, shifting towards the red end of the spectrum. This stretching effect is called redshift, and the farther away a galaxy is, the greater its redshift.
So astronomers can measure the redshift of a galaxy's light to determine how far away it is. It's like a cosmic distance ladder.
That's a great way to put it. And the further up that ladder we climb, the more astonishing the universe becomes.
What do you mean?
Well, when astronomers started measuring the redshifts of distant galaxies, they discovered something truly profound. The universe isn't static, it's expanding. Every galaxy we observe is moving away from us, and the more distant the galaxy, the faster it appears to be receding.
That's mind-blowing. So you're saying that the very fabric of space itself is stretching, carrying galaxies along for the ride.
Exactly. It's like dots on an inflating balloon. The dots aren't moving across the surface, but as the balloon expands, the distance between them increases. But it gets even crazier than that.
There's more.
Yeah. The expansion of the universe isn't just continuing, it's accelerating. Imagine pushing a ball uphill. You'd expect it to slow down as gravity pulls back on it. But observations of distant supernovae exploding stars that act like cosmic mile markers suggest that the universe's expansion isn't slowing down, it's speeding up.
Wow. What could possibly cause that?
That's one of the biggest mysteries in modern cosmology. Scientists have attributed this accelerating expansion to a mysterious force called dark energy, an energy field that seems to permeate all of space and counteracts gravity, pushing everything apart.
Dark energy. It sounds like something straight out of science fiction.
It's a concept that still has scientists scratching their heads.
Mhm.
And you know what? It gets even weirder, because dark energy isn't the only invisible player in the cosmic symphony.
What else is there?
Astronomers have also observed that galaxies are rotating faster than they should based on the amount of visible matter they contain. It's like there's some unseen stuff providing extra gravity to hold them together.
So there's something invisible out there, something we haven't been able to detect directly that's affecting the movements of galaxies.
Exactly. This invisible stuff is called dark matter, and it's thought to make up the vast majority of the universe's mass.
This is incredible. It's like we've only just begun to scratch the surface of understanding the cosmos. We've discovered planets around other stars, mapped out the structure of our galaxy, learned that the universe is expanding at an accelerating rate, and encountered these mind-boggling concepts like dark matter and dark energy. But amidst all these incredible discoveries, one question still lingers in the back of my mind. Are we alone?
That's the ultimate question, isn't it? And while we haven't found definitive proof of extraterrestrial life yet, the sheer vastness of the universe makes it statistically probable that other forms of life exist out there.
So the search continues.
It does. And every new discovery, every tantalizing clue brings us one step closer to answering that profound question. Are we alone?
This deep dive into astronomy, the solar system and beyond, has been truly amazing. We've journeyed from our own planet to the edge of the observable universe, encountering mind-boggling concepts and incredible discoveries along the way. What's the most important takeaway from all of this?
I think the most important thing to remember is that we are part of something much greater than ourselves. We are interconnected with the cosmos in ways we are only beginning to understand.
Absolutely. It's humbling, awe-inspiring, and more than a little bit terrifying all at the same time. As we wrap up this deep dive, I'm left with a sense of wonder and a thirst for more knowledge. What a truly incredible journey. Until next time, keep looking up and never stop exploring.